Hey, trig class, in section 8.2, we're going to continue on with the inverse trig functions, looking now at inverse secant, cosecant, inverse cotangent. All right, and then we're going to end up using these inverse trig functions all together by the end. All right, notice inverse secant, inverse cosecant, inverse cotangent. These are the reciprocals of cosine, sine, and cotangent respectively, but be careful because they do have different domains in their reciprocal friends sometimes, where secant does not. And secant is the reciprocal of cosine, so its inverse is defined still only between 0 and pi, just like inverse cosine was. Inverse cosecant, that is the reciprocal, cosecant is the reciprocal of sine, and it too is defined between negative pi over 2 and positive pi over 2, just like inverse sine was. All right, but inverse cotangent, that is the reciprocal of tangent. Inverse tangent was defined between negative pi over 2 and positive pi over 2, but inverse cotangent is defined between 0 and pi. And again, the reason is because narrowing down these functions to their regions that are closest to the origin, that will produce the entire output. And so you can see with tangent, the region that does it is the negative pi over 2 to positive pi over 2. Those are vertical asymptotes that give one whole entire region for the tangent function. But when I switch to cotangent, you can see that it's broken apart. That I do have the negative, the 0 down to negative infinity. I have the infinity, but I'm crossing over a vertical asymptote. So to avoid that, I'm just going to slide over to 0 to pi, and now I don't have to worry about a vertical asymptote being in the middle of the region I defined this. So that's the reason why we have this shifting in the cotangent function, and so why we go between 0 and pi rather than negative pi over 2 and positive pi over 2 like tangent did. So cotangent kind of disobeys and kind of breaks away from its reciprocal as far as the inverse trig functions ranges go. All right, so when I'm looking for the inverse secant, inverse cosecant, inverse cotangent, I think of it via the cosine. So if inverse secant equals 1, the reciprocal of 1 is 1, so where does cosine equal 1? And I look on the unit circle and I see cosine equals 1 when the angle is 0 radians, so therefore secant equals 1 when we are at 0 radians. So inverse secant of 1 is 0. So I can do it that way. When I have cosecant, inverse cosecant, where is cosecant equal to 2? So I could ask that, but it's easier to use the unit circle if I use the reciprocal sine and change 2 to its reciprocal of a half. So where is sine equal to a half? And I'll look for that on the unit circle. Sine is now the y coordinate. All right, so cosecant, I'm in this region. Where is sine equal to a half? Positive a half. Sine is the y coordinate, that's right there. So pi over 6 is the angle that makes secant equal to 2. All right, where is cotangent equal to the square root of negative square root of 3? That would be the same place where tangent equals the negative square root of 3 over 3. That's the reciprocal of the square root of 3. All right, or you can think of it as negative 1 over the square root of 3. Now, again, this has to be between 0 and pi. So where is tangent equal to negative 1 over the square root of 3? Between 0 and pi. So again, tangent is negative in quadrant 2. That's, again, between 0 and pi. That's where we have to live. So tangent's negative here. That's, again, falling left to right. And negative 1 over the square root of 3 means the y coordinate's 1. The x coordinate is the square root of 3. Y coordinate's 1. The x coordinate is the square root of 3. So there's the one that we want, the 5 pi over 6. So there's our answer. Okay, so you are using the reciprocal functions, cosine for secant, sine for cosecant, tangent for cotangent, and using the unit circle to help you come up with these answers. All right, on the TI, I don't have an inverse secant button. I don't have an inverse cotangent button. So what I have to do is do the inverse, say for secant, I'd have to do the inverse cosine of the reciprocal of this. So instead of 8, I would do 1/8. And there's my approximation. For inverse cosecant, I would do the inverse sine, again, of the reciprocal, so negative a half. All right, and then for inverse cotangent of these values down here, I would do the inverse tangent of the reciprocals. So you can see they're showing use a calculator. There's what they got for the inverse sine. There's their 1.37. All right, now these types of problems are a little bit trickier than the rest because you're expected to be able to come up and do right triangle trigonometry. So this is where it's very important that you understand what an inverse trig function is. Inverse trig functions are angles. If you can get that down, these types of problems are not bad. If you can't get that down, these problems become really tough. So there's what I'm told. This function, this trig function, is different than the inverse trig function on the inside. So when that's the case, just go ahead and start drawing a right triangle. All right, just label one of the angles theta. All right, now the angle is the inverse trig function. Inverse trig functions are angles. All right, that means the tangent of the angle is equal to the number on the inside. It's equal to the 4/3, and tangent is opposite over adjacent. So that means the opposite of this angle is 4, the adjacent side is 3. All right, and then the Pythagorean theorem would show you that this hypotenuse is 5. Okay, and now there's an angle, and I'm looking for the sine. Remember, this is the inverse tangent, so this is just the sine of theta that I'm being asked to do. So this is back to like right triangle trig at the very beginning. Opposite, which is 4, over hypotenuse, which is 5. So there's my value. So if I understand that the inverse trig function is an angle, I can use that the trig function that this is the inverse of to set up the right triangle to let me find that third side that will let me find any trig function of this angle. When I say this angle, I mean the inverse trig function that we're given. Let's do the same thing for this one. Cosine of the inverse sine. So the inverse sine is the angle. That means the sine is negative 1/3, and 1 is the opposite, 3 is the hypotenuse. All right, for sine, 3 is the hypotenuse. So they're drawing this picture because they want it to be, because it's negative, it's in quadrant 4, so they're drawing it over here in quadrant 4. And so doing, again, the Pythagorean theorem, this is my negative 1, this is my hypotenuse, it's 3, it's always positive. Then this side, again, because we're in quadrant 4, would have to be a positive square root of 2 over 2. It has to be positive because to be in quadrant 4, you have to go right and then down. So right is x and y, or sorry, left and right is x, up and down is y. So right would be positive x, down would be negative y. So that's how we know that we have a positive square root of 2 over 2. All right, and then we're looking for cosine. So that's the adjacent side of this triangle divided by the hypotenuse. So there's where the 2 square root of 2 over 3 is coming from. A tangent of the inverse cosine. So again, we're going to let theta equal the inverse cosine. The angle, inverse trig function is an angle. The angle is the inverse trig function. So cosine is negative 1/3. That's adjacent. That's hypotenuse. Again, hypotenuse will always be positive. So cosine is the x-coordinate. That means we're going to the left because it's negative. So that's a negative 1. And then doing the Pythagorean theorem again, we get 2 square root of 2 for that number. And then we're looking for tangent. Tangent is opposite 2 square root of 2 over adjacent. Remember, that's negative 1 since we moved to the left. So that's a negative. It's 2 square root of 2. All right, you can also remember tangent is the slope. So that slope of that line would be negative if it helps you to think through it that way. Just got to make sure you get your signs right.